welding, so to combine different parts together without bolts. And there are different welding techniques. So today we are still using drilling and bolts very often to make composite parts and metal parts. And this is an elevator in carbon epoxy. So it's a beautiful product, very lightweight, but we have to put in all these bolts. Actually, this product is bonded with an epoxy adhesive, so you would say it should be good enough. But the authorities, they mandate the use of bolts. And welding is different. So welding makes it possible to eliminate or reduce the amount of fasteners, so less drilling, less bolts. And bolts are expensive in composites. For carbon, you have to use corrosion-resistant steel or titanium. Those are not cheap. And what we use in aerospace right now is ultrasonic welding, resistance welding, induction welding, and there's a new one being developed, conduction welding. And I'd like to start with ultrasonic welding. Very simple technology used for many things, but also for toys of children. And the way it works is to basically push two parts together, hit them with high frequency, like this, and melting the interface. Very elegant technique, 35,000 hertz, less than 1 second. We've been using this for example, for a Dornier 328 part, a protection plate on the fuselage. And that's the machine there, ultrasonic welding machine on a table. And it welds little pieces onto a thermoplastic reinforced laminate. And the connection between the pieces is truly 100%. So if you take them apart, you're breaking the fibers. For floor panels, it's used as well. So the inserts that are welded by this gentleman, they have some sharp edges at the top and the bottom that melt during the welding, and they melt and connect to the top and the bottom skin of this panel. So basically you're connecting this piece to the two thermoplastic skins of this floor panel. And here's a movie from the University of Delft. You may have read in a magazine that people are trying to develop continuous ultrasonic welding for welding parts together in a serious manner. So two products have been connected with ultrasonic welding on a robot. On an aircraft, there are many panels that have to be connected. So if it's feasible, and it still has to be proven to do this with ultrasonics, it would be an elegant way to connect parts together on a large scale. Then there is resistance welding. Third technique is we have two parts. We take a strip, put it between the two parts, then apply pressure and electricity from a plus to a minus. And this strip is a resistance element that gets very hot very quickly and then basically welds together. This is a piece of the wing leading edge on the A380, which is 28 meters in length. The tip looks like this. The root is much bigger. And the essence is to have ribs that are made in a press. The skin is co-consolidated using prepreg. And then we have, you may see here, a little strip that runs around to here, and it's actually pushed against the skin, and then electricity is flown through this strip, and it's melting this together. On this side, you can even see the polymer coming out. It's being squeezed out. So we have instead of drilling and riveting, we are welding together, reducing the amount of labor to make this part. To do this, you have to prove to the authorities that it's feasible. So the first thing to do was to have it flying on a product. And the product was a door on this aircraft next to the landing gear. And this product was welded with this welding technique, resistance welding, and then flew for several years. And then it was taken off the aircraft and inspected to see if the welds were still like new, which they were. And with that proof of technology, Airbus was approached. And Airbus was developing a new wing leading edge at the time for an A340 aircraft, had an aluminum leading edge, and on paper they had discovered that if you could weld this product in composites, it would be a good business case. So the advantage of welding is it's a low-cost joining, and it is homogeneous. There is no dividing line. So the two parts have the same material. And the result is that the authorities accept this as a serious joint. And I'd like to show you this picture under the microscope. So at the top, you see the little fibers in the rib. So basically it's this rib here. You see the fibers in this area here, top of the picture. Then in the middle of the picture is the welding strip. The white color is a metal mesh. It's the resistance element. And the dark color is the polymer material. And at the bottom is the skin of the wing leading edge. And if you look closely on the picture, you do not see a dividing line if you go from the top to the bottom. It's a homogeneous joint. And this type of picture is what convinced the authorities in the UK and later in the US to accept welding as a joining technique without drilling holes and without bolts. And this is what it looks like on the outside. It has to be nice and smooth. The third one is called induction welding. It's a different technique. And actually we have a license for this from a small Dutch company called KV Composites Group. And this is the company that has pioneered induction welding. And what is induction welding? It means that you take your composite material, you put a robotically held hand, and this hand creates an induction field in the composite material. So it has a copper coil inside. The yellow part has a copper coil inside. It creates the green lines, so induction fields in the composite material, and it gets very, very hot and it melts the polymer. And if you do this in a controlled manner, you can join products together. So if you have a robot, you can move it and create a continuous joining. So once again, the yellow is the induction, the gray is two pieces of material. So there's the skin, horizontal, and there's the rib, this one, with a flange over here. Yeah, and we want to weld this together. So if you just turn on the yellow spool, everything becomes hot and melts. You do not get a good product. You want the outside to remain cold and the inside to get very warm to weld. So you add some tooling material. Tooling on the outside with a heat sink that will absorb the temperature, and on the inside a way of applying pressure. And the way it works, the black piece that you see is a rubber, and below the rubber we are pushing against it with an inflatable rubber tire, basically. And then you get the heat zone where you want it, so not on the outside, but on the inside of the product. So this was some development effort starting in 2003 to develop this technology with different partners, and in the end it was successful. So you start always, when you do this new technology, you have to start with the small pieces on the left, and then you go into larger components. And once again, here is a picture and a microscope. If you go from the top to the bottom, you see only one material. So there is no dividing line that you can find between these materials.